Thank you for the introduction, and I'm very happy to be here today. So I have 10 minutes, so let me jump right into this. I am an engineer and a scientist, and for many years I've been interested in sensor networks for geospatial applications, for soil and for water. And I want to make a couple of points as we talk about data and the environmental sciences and sustainability, that for this to really take hold, data needs to be at scale, and the technologies are there or are fast arriving. The hardware technologies, that's the world I come from, is there. Semiconductors computing has almost become a commodity. There have been major advances in sensing technologies for soil, for water. They're still somewhat expensive, even today. For instance, a good soil moisture sensor costs $250. But if you look at scaling, they will become cheap very soon. The challenge here is that for all of this to work, for us to be able to use data, to use artificial intelligence, et cetera, data has to be collected, curated, and made available in huge public databases available to everybody. If you look at areas where AI has been a success, right, in every single instance, when I call it success, in a large way, that it's changed for things for the public good. It has relied on huge training databases that are available to all. So for instance, handwriting recognition, image recognition, this image recognition came out of this major database that was started by a young assistant professor at that time, Fei Li, at University of Illinois Urbana-Champaign, called ImageNet. Right? And that was the database that everybody could train. That was the time when there was a realization that AI was not just about algorithms, but the collection and curation of data. If you look at something more recent, which is another major success for machine learning and AI, is protein folding. Again, it relies on enormous databases that were made available by the National Institute of Health and so on. So for this business to succeed, I strongly believe that that's a direction we all need to sort of move towards in a coordinated way. And, I started got interested in this work because we had this vision of a geopixel, right? So think of a little piece of land or water, and stacked against this pixel is a whole host of data. It could be metadata such as population pressures, industries, etc. It could be soil chemistry data. It could be environmental chemistry data, water data, etc. And then once you have this whole row of data, you can then develop physical models or physical models that also depend upon societal inputs to then develop predictions, right? That's sort of the way I look at this. I'll briefly talk about a couple of areas that I have been involved with. The first one is in the area of soil measurements for agriculture and for food security and for terrestrial ecology. This is centered around a large USDA and NSF center called AI Farms. It's led out of UIUC, University of Illinois Urbana-Champaign, and I am a co-PI from the University of Chicago, which is a partner. It's an ambitious goal to try to use artificial intelligence and data to develop better biogeophysical models for soil cycling, for nutrient cycling, for carbon, nitrogen cycling, and develop a model for food production efficiency. So if you think of it like a chemical engineering system, right, you have resources coming in, that's sunlight, water, fertilizer. You have some stuff going on in the soil, and that's an interaction between the root, the soil chemistry, and the microbes that exist in the root or in the soil. And then the output, which is the biomass, the crops that are produced. And the other output is the effluent of, fertilizers that have not been used that then goes off, into tile drains or with water runoff, etc., which then goes and contaminates the riverways, etc., right? So trying to develop accurate models for this, using data, using machine learning, and using sensing, is the goal of AI farms. And it's a diverse group of people, from computer scientists, engineers, soil scientists, agronomists, economists, and so on. This is an example. For instance, we've, for the past 3 years now, we've built a buried wireless sensing network in a working farm. This is in the Chicagoland area. We bury these sensors, and they have little wireless units. We use a low-power IoT setup called Sigfox or LoRa. Some of you may be familiar with these terms. But it essentially allows us to map at high resolution things like soil moisture, things like electrical conductivity, etc. And then we try to relate it to terrestrial ecology models. I'm not an expert there, but I work with colleagues in that area. So this is a pilot that's been going on. These things are called WUSNs, Wireless Underground Sensor Networks. They are coming up big and have been made available because of development in wireless technologies, sensing technologies, and just microelectronics. The second area is something we have been working on since 2017, and this is where also the ubiquitous Priyank makes his appearance. I worked very closely with him on this project. He's the one who actually, led this project and jump-started it. But we have been mapping surface water quality in rivers since 2017. Shreya was also involved. She's here. But I'll show you some examples of what high-resolution mapping can do. It's very simple. We use commercial mobile water sensors. They measure things like 14 parameters, pH, volume water content, electrical conductivity, dissolved oxidative matter, and a whole host of other things. The GPS equipped, we rent a boat. The boat does a sortie. You measure all this stuff. When you come out of the boat, you've got GPS coordinates and a whole bunch of parameters, and you can develop heat maps, right? And you do that in a consistent basis over seasons, over months, over years, and you get patterns emerging, right? So I'll just show you a couple of examples in the picture on the top right. This is a paper mill on the banks of the Godavari in Rajahmundry, and since 2017, we've always measured that the pH, the dissolved oxidative matter, those numbers were out of whack in the Godavari, very close to that plant, which was, I believe, South Asia's largest paper mill. And then I was pleased to learn that in April 2022, the government has actually, brought that paper mill to notice and is investigating it for pollution. The picture in the bottom shows another example of how you can do water management. This is the Yamuna River south of the Wazirabad barrage that's in Old Delhi. And what they do is sometimes they open the barrage, let fresh water in. As many of you know, that area of the river is extremely polluted. And this really shows that once you open the barrage, initially there's sort of fresh water, then you close it, and over days, the drains from Delhi, which is on the left bank of that river, facing this picture, start dumping their effluents. That peaks in the evening when people come back home. But then after a few days, it ends up becoming like a polluted lake, right? So this kind of information can help quite a bit. We were also interacting with local fishermen and villagers and so on, and it's even gotten to the point where the fish will go to areas that are less polluted and so on and so forth. But those correlations are not quite worked out yet. And then we've also shown ways that you can use machine learning models to predict things like water quality indices using instantly measurable parameters and then using some models and so on. And more recently, and then the pandemic shut us down, and then we've revived this most recently with a grant through the Windlass Foundation. And we've started measuring now in the Uttarakhand area. And again, over here where we are headed is that we're finding that there's a tremendous amount of data collected by the CPCB, by state agencies, etc., for water, but it's all scattered in PDF formats all over the place. What we are trying to do is convert these to machine readable form and then putting it in the sort of geopixel stack that I've shown. Shown here for just as an example is in the Rishikesh area. You can see that there is a river, the Chandrabhaga River comes and meets the Ganga. The Ganga is, because it's very fast flowing, the water is really clean over there. It's bathing water quality, right? But the river brings with it some stuff that from industry pollution, right? This is where the metadata becomes important. And at the confluence, there are hotspots of pollution. But again, it's very quickly diluted because of the speed of the river. So this is just one example I wanted to show how different data pieces map onto each other. And we're trying to develop formal ways of making interpretations from these. So that's pretty much it for my talk. And I really want to emphasize, the point that technology has come to the point where all this is possible, but this massive, I emphasize again that massive amounts of data really needs to be available, accessible to all. And the third point I'll make is that I come from this very science engineering background, and engineering fields have specialized themselves over the past 50 years by going deep in very siloed ways, right? Building bridges, building spacecraft, stuff like that. But the major problems that face us, right, things of climate, sustainability, and so on, it's very difficult, for engineers to be able to have a major impact unless they are able to broaden their interaction and education. And so I was, very happy to hear some of the discussion that went on earlier this morning among the four academics in that session. I think coming from the engineering side, this is the direction that I think we're trying to push very hard as well, and is one of the areas of focus of the U Chicago Delhi Center as well. Okay. With that, I'll finish my talk. Thank you.